All right, hello everybody. So welcome back to 10600 Math for Machine Learning. So let's get started on today's class. So the first thing I wanted to talk about were the exercises that you guys did on Monday. So everybody did pretty well on them, which is great. One of the exercises I wanted to take a look at. So this was, you were asked to take the differential of the expression XX transpose. So this is just the product rule. It's x times dx transpose plus dx times x transpose. And the order here is important, right? Matrix multiplication is not commutative, so you have to keep the terms in their original order. I'd like to first point out that this is a really simple derivation and a really simple expression. Now, some people have asked, what's the point of using this differential notation instead of the old-fashioned d by dx notation or even component-wise derivatives? And this example is a perfect illustration of the benefit. If we wanted to write the derivative of this expression in traditional notation, what we'd have to say is, so we could set y is equal to vec of x, and z is equal to vec of x transpose, right? So if you remember, vec is the operator that takes a matrix and strings all of its elements out into one big column vector. And then what we'd have to ask for is what is dy by dz, right? Now, this is in our n squared, right? Because x was an n by n matrix. XX transpose is also an n by n matrix, so this is also in R n squared. So this is a matrix, right? It's a Jacobian of a transformation, and it's an n squared by n squared matrix. And so if you want to write it down, let's say n is 1,000, right? These things take 1,000,000 entries to write out. This thing takes 10 to the 12 entries to write out. So we're talking like multiple terabytes of data even to write this out for a perfectly reasonably sized 1,000 by 1,000 matrix. And if you want to write down an expression for this thing, if you're feeling masochistic, I invite you to try it. It's going to involve stuff like Kronecker products and other crazy stuff like that. So there is, really working with this is just painful in the original notation, and it's nearly trivial when we do it in the new differential notation. The other way that you could do it, right, is to ask what is partial yi with respect to zj, right? And so, yeah, again, I'm not going to try and write that out because it's a pain. You are almost guaranteed to mess up indices if you try and derive this. And it's got lots of annoying summations all over the place, right? The other thing, actually, if you're going to do it this way, it's probably better to ask what is the derivative of x transpose sub ij with respect to x sub kl. That at least saves you from multiplying out the indices. But even to write, yeah, it's annoying, so I'm not going to try and write it out. So that was what I wanted to say about the exercise. As always, please feel free to ask questions during class about the exercises if there are any other things about the exercises that didn't make sense. All right, so now let's take a look at the lecture notes for today. So the first thing I want to talk about is continuous random variables, right? So far, up until today, all of the random variables that we've dealt with in this class have been discrete, and they took on one of a finite set of values. So if you want to think of a length or a height or an intensity or any of a lot of other physical quantities, it makes a lot more sense to think of the random variable as being continuous, a real number or a vector in R3 or something like that. And the first way to deal with any continuous random variable is to discretize. So you can pretend that your real numbers are lengths measured in microns, or double precision numbers stored in IEEE double format, right, which is 64 bits. So there's a lot of possible discrete values, but conceptually this is the simplest way to think of continuous random variables, and it's always a good fallback way to think about them, because none of the math changes. You're just dealing with potentially impractically large probability tables. What we're going to do for the rest of this set of lecture notes is go through possibly a somewhat complicated set of definitions that lead to a simple conclusion. And the simple conclusion, not to give away the punchline, but the simple conclusion is basically that you can manipulate probabilities of real numbers almost exactly the same way as you can manipulate probabilities of discrete random variables. And so for example, you can write, Bayes' rule the same way. P of y given x is the same as P of x given y, P of y over P of x, right? Like all of these things, they still work, but the underlying meaning of the expressions, so the mathematical expressions look the same, but the underlying meaning of the expressions is different. And so we're going to go through today's lecture notes in order for you to know what the meaning of all of these underlying symbols are, because not knowing it can lead to lots of confusion. All right, so let's get started. So the big difference between a continuous random variable and a discrete one is that it makes sense to ask for the probability that your discrete random variable takes a particular value, right? That could be 0.01 or 0.7, right? It could be any number between 0 and 1. By contrast, if you have a real number, the probability that it takes on any particular value, right? Like the probability that the length you measure is exactly pi is 0, right? Not just small, but 0. If it were anything larger than 0, then when you added up all of the probabilities of the infinitely many real numbers, you would get an infinite total probability when you're supposed to get 1. And so it has to be 0, and the total probability is 0 times infinity. Now, 0 times infinity is not really helpful, so we need some other approach. We can't talk about the probability of a real number. And what we talk about instead is what's called a probability density. And the probability density is actually just a differential, exactly like the differentials we've been working with in the past unit. That's why we did that unit before we started talking about continuous random variables. And so here's an example, right? You can say that the differential probability that the random variable x is around the assignment little x is equal to some expression times dx. Right? This particular expression happens to be the Gaussian distribution, and we'll get to be great friends with Gaussians in the second mini. But for now, forget what this actual form is, and just note that it's a real valued function times dx. What does a probability density mean? It means that if you want to find actual probabilities, you have to integrate. So to find the probability of an event E, right? So an event is some set of possible outcomes for x, like maybe that x is between 0 and 1. We integrate. So the probability of the event is the integral over that event of the differential probability. So it would be something like integral over e of this expression dx. And so if you want to know whether x is between 0 and 1, you integrate from 0 to 1, and you find some number. And if you want the probability that it's between minus infinity and infinity, you integrate over the whole real line, and that better be 1. Right? So a probability density, dp, is the real version of a probability function, of a probability table. Right? And you can actually make an analogy, just like in a discrete random variable. You could make a table over all of the values of two random variables x and y, right, and fill this in with numbers like 0.03, right? In the continuous case, you can make a graph with axes. Okay, I'm actually going to swap so that it is x and y, so that the axes are x and y here, right? And you can make some function. So I'll draw, a contour plot of that function, right? Like that. And if you evaluate it at some particular point, it'll be some number like 0.03, right? And so this two-dimensional function is exactly analogous to this two-dimensional probability table. And the only difference is that there are infinitely many settings for x across the horizontal axis and infinitely many settings for y across the vertical axis. I have a question before we go on about this. I have a question about the exercises. It wants to know, why can't d of x transpose be represented as d, so this is equal question mark, dx transpose x plus x transpose dx. Right, so this here is equal to this, except that we've swapped the order of terms. And matrix multiplication is not commutative, right? So if you swap the order of the terms, you get something different. I invite you to try it, right? Just try picking two random matrices in MATLAB or NumPy and multiply them in two different orders, and you'll get different answers. So here we're multiplying the terms in one order. Here we're multiplying them in the opposite order. And so we get something different, right? So I'm going to X this out. You can't have that because the terms are in the wrong order. All right, so going back to continuous probabilities, right? So we've got this for discrete probabilities, and the analogous thing to a two-dimensional table is a two-dimensional function, a function from R2 to R for continuous random variables. Same thing works for vector-valued random variables. You can still write for a vector-valued x, the differential probability that big X equals little x is equal to f of little x dx. And if you want to find the probability of an event, you're going to have to do a multiple integral in this case, right? So for example, if we're in R squared, we'll do a double integral. The integral for x1 from 0 to 1, for x2 from 0 to 1. That will find us the probability that we're in the box 0, 1 cross 0, 1. And as shorthand, we'll still write P of E is integral over E of f of x dx. And this will be the same for the single variable and multiple variable case, and we'll just know whether x is a scalar or a vector, and therefore whether we have to do a single or a multiple integral. Right? So going back here, we could integrate over this box to find P of E. Okay. So for notation, right, we have the long notation dp of x equals x is equal to f of x dx. We can also just write dp of little x, so that leaves the big X implicit. And we can even drop off the argument x and just say dp is f of x dx, right? And that's when we have a the differential probability is a function of the differential element of area or volume in x. Length, area, volume, whatever it is, depending on the dimensionality. And if we have something like this, right, dp equals f of x dx, we'll actually sometimes just write p of xy is equal to, I guess here in this case, I did it with a two-variable one, so dp of xy is equal to f of xy. We'll also just write p of xy is equal to f of xy. Right? So that means that this p, for continuous random variables, it means the part of the density that leaves off the differentials x and y, right? These differentials. So this is a notational shorthand, and it looks now just like the discrete case, right? You could write an expression that looks exactly like this in the discrete case, just that x and y would range over some discrete set instead of over, say, the real numbers. So this completely hides the fact that we're working with differentials, but it's always a good idea to remember that the differentials are still there, because if not, you can make errors. So for example, for a continuous probability density, it's perfectly fine for the f to be bigger than 1, so long as the integral, right, it can't be bigger than 1 over a large area, but it can be bigger than 1 over a small area, so long as the overall integral is still 1. Whereas, of course, it doesn't make sense for a probability to be bigger than 1. So a density can be bigger than 1, a probability cannot. So that means that we can, with continuous random variables, use exactly the same notation that we would have with discrete ones, but we have to remember that the underlying math is different. We're dealing with a density instead of with a plain probability. All right, so just like probabilities, we can write conditional probabilities, and just like densities, we can write conditional probability densities. So here, the dp of big X equals little x given big Y equals little y is going to be some function that depends on both x and y times dx. So note, this is a probability distribution over x. Y is fixed, or maybe little y is a variable, but for each value of little y, we have a probability distribution over x. And so there's a differential in x, but there's not a differential in y. That means it makes sense to integrate with respect to x, but not with respect to y. So for example, we know that if we integrate over x, f of xy, we're going to get 1, no matter what y is. But no such identity holds for y, right? There's no law of total probability for the argument to the right of the conditioning bar. And we can, just like before, write dp of little x given little y, leaving the random variables big X and big Y implicit. And we can also just drop the d and talk about the part without the differentials. So like I said, the rules are almost the same now for working with continuous random variables. We have a sum rule and a chain rule and a Bayes rule. They look a little bit different. So I've written the forms here in the lecture notes. So for example, in the sum rule, we're doing an integral instead of a sum. And in the chain rule, right, dp of xy has both a dx and a dy in it. dp of x given y has just a dx, and dp of y has just a dy. So we have a dx and a dy on both sides, and the two expressions are equal. Right? And we can drop all of the differentials and say p of xy is p of x given y times p of y. And it looks just like the chain rule from regular probabilities. Same thing with Bayes' rule, right? It looks exactly like this, but you have to remember that this version is hiding a bunch of differentials that are in the fully accurate version. All right, so one last warning is that with continuous probabilities, unlike with discrete ones, there are a whole lot of really weird behaviors having to do with the fact that integrals are weirder than finite sums, and having to do with the fact that it really matters what coordinate system you use when you talk about continuous random variables. And so I'm not going to talk about it here, but I encourage you to click on the link to the Borel-Kolmogorov paradox, which shows you all of the things that can go wrong if you're not very careful about how you work with continuous probabilities. And so what I recommend is that for intuition, you always fall back on the discrete case. Right? Think about discretizing all your continuous random variables and writing a joint probability table. And that doesn't work for computation, but it works for intuition. Right? You can still do all of the probability calculations like Bayes' rule in the discretized version. And then you can look and make sure that everything that you're doing makes sense. So in particular, if you look at the Borel-Kolmogorov paradox, what happens is that there's two different ways to discretize a sphere, and those two different ways are implicit when you're working with the continuous probability and when you're working with the continuous probability. But as soon as you discretize, you'll see that the two discretizations are different and that they should lead to different answers. All right, so that is continuous probabilities. As usual, please send us questions if anything wasn't clear, and I'll move to the next set of lecture notes. Actually, the very last set of lecture notes for the entire mini, which seems like an achievement. All right, so all of this is intended, everything that we've done so far this course has been intended to do to give you guys math that's useful for doing machine learning. And we've barely done any machine learning all semester, right? The most we did was learn a Fisher discriminant. So now let's just start to think about how all of this math lets us do machine learning. And to do that, we're going to look at a very simple statistical inference question. Let's suppose you flip a coin 20 times. It comes up head 15 and tails the remaining 5. Do you think the coin is fair? And I encourage you to, write down an answer for yourself. In particular, not just whether the coin is fair, but like what odds would you give somebody if you were going to bet whether the coin was fair or not? And so statistical inference means finding numerical answers to this sort of question about randomness. Quantitatively, how much evidence do we have to support or reject a conclusion like whether that coin is fair? So to do statistical inference, we'll make a model. A model is, as always, a guess about how the world works. So for a coin flip, we can model it as saying the coin has probability P of coming up heads, right? And for a simple event like a coin flip, that's basically the only model we can make. But the possibilities can get far more complicated as we get to more complicated systems. So let's say we want to model several coin flips, for example. We might say that each flip has the same probability P. We might not know what P is, but we think it's the same. Or we might say that the first 10 flips have probability P1 while the next 10 have probability P2. Maybe somebody swapped out the coin halfway through the experiment. We could even say the first flip has probability P, but every subsequent flip depends on the outcomes of previous flips. Let's say every time we get heads, the probability of future heads increases a little bit. This is a really weird coin, but it is a potential model of the world. And actually, if you watch people bet in a place like Las Vegas, you will see that they actually sometimes implicitly use models that look as weird as this. So the first one, saying that every coin flip is independent of every other coin flip and has the identical distribution, meaning has probability P of coming up heads. That's called IID, or independent identically distributed, and that is by far the most common model that people use. It's always worth remembering, though, it's just a model, and as such, it can be wrong. All right, so our model has a parameter p. In general, models will have more than one parameter. You could have thousands, millions, billions of parameters. And we might, if we're lucky, know the values of the parameters, but often the question that we have to answer is to figure out the values of these parameters from data. And so we better have repetitions, right? So in our IID model, we better have, 20 flips instead of one flip. Otherwise, we don't have much chance of figuring out anything about the parameter, about the probability. And so we'll assume that we're in a world like that. We have a model. The model has some parameters. We get IID draws from the model, meaning repeated experiments that have the same distribution. And we have to figure out the parameters. So before we see any information, we might have a guess about the parameters. And we can distill that guess into a prior distribution, which is just a probability distribution over the parameters. And often the parameters are continuous, and so that means that we have a density, right? That's why we need to talk about continuous densities. But it can be a discrete parameter as well. And the prior distribution is typically fairly broad, right? If we knew a lot, we would not have the need to do an experiment. So for example, for our coin, we might just know that its probability is somewhere between 0 and 1. We might think alternatively that it's somewhere closer to 0.5, right? Or we might think that, this guy with the coin doesn't look very trustworthy, so we have a higher probability on it being biased. And then once we see the data, right, we start with this P of parameters, right? And what we would like is to get P of parameters given data, right? So that means that we see some data. The data depends on the parameters. We condition on the data, and we want the posterior distribution, the distribution after seeing the data on our parameters. And unsurprisingly, we can find the posterior with Bayes' rule, right? So P of parameters given data is P of data given parameters times P of parameters divided by P of data, right? So here is our prior, here's our posterior. The two new terms, this one, P of data given parameters, this comes from our model. In fact, it's more or less the definition of a model that given a set of parameter values, it tells you what the distribution over the data is, right? If it doesn't tell you that, then it's modeling some other phenomenon besides the experiment that you're conducting. So this term is called the likelihood. And qualitatively, it tells us how happy any given set of parameters is, explaining any given set of data, right? And so that means if you look at the form here, the likelihood term is telling us that parameters that make the data that we actually observed more probable are themselves more probable. And that's something that takes a little thinking to wrap your head around. Excuse me. Right? So in some sense, what's happening is post hoc, we're optimizing our explanation to fit the data that we saw. Right? We're taking the explanation that makes what we saw most likely. And it might not be a priori obvious that that's the right thing to do, but so long as you believe Bayes' rule says that, parameters that were a priori more likely are also more likely a posteriori because this term will be larger. And parameters that make the data more likely are also a posteriori more likely because this term will be larger. And typically this term outweighs this term. And so this is the effect that really counts. Parameters that make the data more likely are themselves more likely. Now, this last term, P of data, is a pain. In a lot of situations, we can't calculate it. And so what we're left with, right, it doesn't depend on the parameters, right? This is P of data marginalizing out the parameters. And so P of parameters given data is still proportional to, right, P of data given parameters times P of parameters without the P of data term here. And so we can get the relative ordering of different sets of parameters under the posterior, even if we are not able to figure out P of data. In other words, even if we're not able to normalize this and get an actual probability distribution or probability density. And this here is an important equation. It may well be the single most used equation in all of machine learning. So since it's important, let's write it out in symbols, right? So we have x, which is the list of all of our outcomes, x1 through xn, of n IID repetitions of an experiment. Each one of the xi's is a random variable, and so therefore so is the whole data set x. And by independence, we write p of x is the product of the p of xi's. That should actually be p of x given a parameter value is the product of p of xi's. So we're going to write theta for our parameter. Theta could be a single real number, or it could be a vector of lots of parameters like the weights of a deep neural network. And so with this notation, p of parameters given data is proportional to the prior distribution over parameters times the likelihood, which factors because of IID-ness, into the product of p of each individual data point given our parameters. So the exciting conclusion. In the coin flip example, our model was that each coin flip is independent with probability theta if it was heads and 1 minus theta if it was tails. So our data of 15 heads and 5 tails, and let's suppose we have a uniform prior for theta. Then p of theta given x is the prior, which is uniform, so it drops out, times the likelihood, which is 15 copies of theta and 5 copies of 1 minus theta. And if we plot this, it looks like this. And so what does this say? It says that under our posterior, so here's a half, right? So the coin is highly likely to be somewhere over here, biased towards heads, but it's not certain. There's still a tiny chance that we just got really lucky and the coin was biased a little bit towards tails. And we can get the exact value by numerical integration, which isn't a problem in one dimension, even if it is if you have a 1,000-dimensional set of parameters. And it says that we have an almost 99% posterior probability that the coin is biased at least a little bit towards heads. All right. So the posterior is a whole function, right, or a whole differential. What if we want to report just a single value for the parameters instead of the entire posterior? The value that makes most sense to report is the most probable one, the one that maximizes our posterior. And so this one's called the maximum a posteriori, or MAP, estimate of our parameters. And as usual, to maximize a continuous function, we can differentiate and set the derivative to 0. Well, we also have to do the usual checks like, does that get us a maximum or a minimum, and could the maximum occur on the boundary of the feasible region? But for now, I'm going to ignore those and just say differentiate and set to 0. And actually, it's common to maximize the log probability instead of the probability. That's just fine because log is monotone, so the maximum is going to be in the same place. And so in our example, right, let's just write it out, right? So we had p of theta given x was not equal but proportional to theta to the 15, 1 minus theta to the 5. So log p of theta given x is equal to a constant, right? Because of this proportional to, the constant of proportionality turns into an additive constant. And then log of this becomes 15 log theta plus 5 log 1 minus, not 8, but theta. All right, now if we take the differential of this, right, d of log p of theta given x, the constant goes away, and we get 15. The derivative of log is 1 over theta d theta, right, plus 5, 1 over 1 minus theta d theta times minus 1, right, because of the minus sign there. And so that's what I wrote here, right? And if we solve that, we get that theta is 15 over 20, or 3/4, right? And okay, so maybe that's not a surprise to anyone. If we got 3/4 of our heads to come up during our experiment, the most likely value for the probability is 3/4, but it's always nice when math agrees with intuition. I want to point out here, right, so we took the log of the probability, and what that did was it turned a product into a sum. And that means that we can use linearity of the differential instead of having to work through the product rule, right? And in more complicated cases, there can be a product of a really large number of terms, and so the product rule could be kind of a pain, and so that's why we take the log, to avoid having to use the product rule. All right. So we used a uniform prior, and the uniform prior leads to a method called maximum likelihood, right? Because if the prior is uniform, it's constant with respect to the parameters, and it drops out of the maximization. And so the only term left is the likelihood, and so we're finding our parameters by maximizing the likelihood. Maximum likelihood you can think of as being the right answer to give to a group of people who can't agree on the prior, because the uniform prior is in some sense the least informative possible prior. It doesn't favor any one value of theta over any other. All right, so our procedure. We start by designing a model that captures all of the potential behaviors for the data. For example, all of the possible values of p of heads. The model has a parameter vector theta, and that's what we want to discover. We assign a prior based on the knowledge we have before seeing data, or we just set the prior to be uniform over a wide range of values of the parameter if we want to minimize arguments. Then we observe the data and use it to compute our unnormalized posterior, and we either normalize the posterior and report the integral over some event of interest, or we maximize over the parameters and report the best value of the parameters. And that's called map if we used a prior, or the maximum likelihood estimate if we used a uniform prior. All right? So make sure that you really have this procedure internalized, because it's going to come up over and over again in any kind of statistics or machine learning. And also, I wanted to warn you about some common mistakes people make when applying it. So the first common mistake is to assume too simple a model class, right? So our posterior is only relevant if our prior was somewhere close to the truth, and our prior can't be close to the truth if we used the wrong model class. And you often see people ignoring this source of error, right? I've seen more times than I care to say a paper say, okay, with 99.983% probability, the following conclusion is true, when if you have half a look at the paper's methods section, you discover that there's really far more than a 0.017% chance that they made a bad modeling assumption. And so usually the best way to do that is just to acknowledge that there's some non-zero probability that the conclusions you get are totally wrong. And you don't know what that probability is, but the more janky your model class is, the more that probability is. Okay, the second is that people will make a nice model and go and collect some data and fit the model and get an answer. And then they'll say, oh, okay, that answer goes and applies to any other sample we might have collected. And to see why that's wrong, imagine standing on the corner of Forbes and Craig and asking people if they know about anonymous functions, right? And I will bet you that on the corner of Forbes and Craig, at least a moderate percentage of people will say yes, they understand anonymous functions. And I will bet that if you go out to a random street corner in a random city in, basically anyone that doesn't have a major university in it, you're going to get a very different answer, right? And so that's called the representativity of our sample. And we need to make sure that we use a representative sample for whatever conclusion we want to draw. The third common mistake is overfitting. So that's basically a case of garbage in, garbage out. If you don't have very much data, you can't expect to fit a very complicated model accurately. And so if you do, well, the results that you get will not be very informative. And the last one, which I'm actually going to let XKCD say for me, is called the multiple test fallacy. The problem with multiple tests is if you try and fit a lot of models to the data and consider only the best one of the models is going to fit well just by blind luck. And so you shouldn't trust the results. Here's XKCD. I will let you appreciate that for a while. Notice the difference in this panel. All right, so the news release is clearly wrong, right? What happened was that the scientists did more than 20 tests. Each one had a 5% chance of making a mistake. And so you expect one of them to make a mistake just by chance. You would be surprised if one of them didn't. All right. So what I'd like to do next is to do an example. And that example will involve, unsurprisingly maybe, the Gaussian distribution. So the expression for a multivariate Gaussian distribution, right, is that dp of x given theta is equal to 1 over the square root of the determinant of 2 pi sigma times e to the minus 1/2 x minus mu transpose sigma inverse x minus mu. Now, you don't need, oh, and I should say dx. All right. Now, this particular form, you don't have to remember it, although I do by long hours of having to deal with it. You don't have to remember it because look it up on Wikipedia, right? You'll find it very quickly. What you should remember is that there are two parameters. So theta here is equal to a vector, mu and sigma. Or actually, let's just call it a tuple, mu and sigma, right? So sigma is in Rn, and mu is in Rn, and sigma is in Rn by n, right? So x is an n-dimensional vector, mu is also an n-dimensional vector, and sigma is an n by n matrix. Mu is going to be the mean of x, and sigma is going to be the covariance of x. That's not, by the way, obvious, but if you work with the Gaussian, if you go through the appropriate proof, you can prove that, in fact, mu winds up being the mean of x, and sigma winds up being the covariance. Now, suppose that, well, okay, so I'm going to do two transformations. One is I'm going to fix mu to 0. So we're going to say now mu equals 0, and then we're going to replace, to make the derivation a little bit easier, we're going to replace sigma inverse by p. Right? And then what we get is dp of x given theta is equal to the square root of the determinant of p over 2 pi times e to the minus 1 half x transpose p x. Again, dx. All right? So, what I'm going to ask you to do is suppose that you've observed a sample x1 dot 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 xn with xi distributed according to that distribution. IID, of course. Can you figure out the maximum likelihood estimate of p given that sample, right? And so just to remind you, what that means is that you're going to want to write out the likelihood term, take the log of it, and then take the differential, considering p to be a variable and x to be fixed, or the sample, xi to be fixed, and set that differential to 0. All right? So this is not going to be a graded exercise, but I'm going to let you guys think about it for a little while. And after you've done that, I will go ahead and run through the derivation myself so that you can compare your answer to mine. Before we let you do that, I want to just give you a picture of what's going to happen. So here, this is an example of the probability density for a normal distribution. I've got a contour plot down here and an ordinary surface plot there. And what I've done, I've kept the mean equal to 0, and I'm sampling some random sigmas. And you can see that what it does, the contours are always ellipses, at least to the limit of MATLAB's plotting accuracy. And different values of the parameters lead to different shaped ellipses. And the picture for what you're trying to do is you get some data that looks like this, and you would like to fit a covariance matrix to get a plot that looks like this, right? And so what's happening here, let's just make this a little bit bigger, right, is that we have fit our covariance matrix, and our ellipses show that the regions of high probability now coincide with where we have data points. All right. So as always, please feel free to ask questions, and I will stay silent for a sec and let you guys work. Can I discuss, I'm getting a question, can I discuss a bit what happens with correlated observations? So if you believe that your observations are correlated, the best thing to do is make a model which explains that source of correlation, right? So a good example of a model like that would be, let's say that we're going to get some variables zi that are distributed as a normal distribution with mean let's say mu and covariance sigma, right? And then there's another variable, let's call it y, which is distributed as normal with mean 0 and covariance, we'll call this sigma z and we'll call this sigma y, right? And then the variables xi are equal to y plus zi, right? And you can make a model that says that you observe the x's, but you don't observe y or z, right? And then the x's are going to be correlated, but you can still treat, there's a z's that are an IID sample, and there's a y, which is corrupting all of the observations at once. And so you still get to use your model that has an IID sample in it. You just have another part of your model that describes the correlation between observations. And so you can still use all of the exact same techniques, right? You write out the probability of your xi given your parameters up here. And you take the log likelihood and you optimize the log likelihood to find the best value of mu, sigma z, and sigma y. Now, you've only got one observation of y, and so you shouldn't expect to get an accurate posterior distribution over y, right? I mean, you don't even have a direct observation of y, but there's only one copy of y floating around in your model, and so you're not going to be able to get this very accurately, so you will have to have a strong prior on what sigma y is. But you could expect to get mu and sigma z accurately, subject to whatever you know about sigma y, right? And the numerics of doing this sort of thing can be kind of painful. And that's well beyond the scope of this course, but that's something that you would very much expect to see in a course like our graphical models course, which is 10708. And as a matter of fact, in the second mini, given that everything is Gaussian, in the second mini of this course, we're actually going to get to where we could estimate a model like this one. So I'll put the problem definition back up and sign off for now until we get another question. All right, so let's see how this answer looks. So, get ourselves some fresh paper. Maybe a whole sheet of fresh paper. All right, so we have that P of x given theta is equal to the product over I of P of xi given theta, which is to say square root of the determinant of P over 2 pi times exp of xi transpose P xi over 2, right? And let's assume a uniform prior over a large region. I guess I should say as well that theta is just the inverse covariance P. All right, so what we would like is to take d of log of P of x given the matrix P. I should really use a different font for this P and this P, but I'm not that good at writing in different fonts. And that is equal to the sum over I of here, this is going to be 1/2 the log of the determinant of P plus some constants that come from the 2 pi that we don't care about. Oh, and this should be a minus here. Minus 1/2 xi transpose P xi, and we would like the differential of that. Okay, so when we go through, the differential goes through by linearity, and we actually know from the last set of lecture notes what the differential of log determinant is, and that happens to be the trace of P inverse dP minus xi transpose dP xi. Okay, so now how do we go about solving this? First, this term, it's a scalar, so it's equal to its own trace of xi transpose dP xi. And then we can use trace rotation, trace of xi transpose dP. And then this whole thing is equal to, trace is linear, so this is the sum over I of 1/2 trace of P inverse minus xi transpose dP. All right. And now we, and we can push the sum inwards, right? So I'll erase the sum. There are n copies of P inverse, and I'm going to push the sum to there. All right. So we want to set this to 0. In order for it to be 0, no matter what dP is, the coefficient of dP has to be 0. So that means that NP inverse is equal to the sum over I of xi transpose, which is to say that P inverse, which is to say sigma, is equal to 1 over n sum over I of xi transpose. So this, again, is maybe not surprising. What we've done is, instead of having the expected value of xi transpose, which is the definition of the covariance, we're having the average of xi transpose over our sample. And so that is the maximum likelihood estimate for sigma. So, I think that's the end of what I wanted to say today. Your next lecture is not a lecture but an exam on Monday. Good luck on the exam. And it's been a lot of fun teaching this semester, and I hope everybody got some interesting math out of it. So good luck on the exam, and I will see you guys virtually on Monday.